Hey friends, welcome to the YouTube channel all about electronics. So in the previous video, we understood the concept of the Gauss Law. So now in this video, we will see the applications of this Gauss Law. So if you have followed the previous video on the Gauss Law, then we have seen the expression of the Gauss Law both in terms of the electric field as well as the electric displacement field. And then we have also seen the relationship between this electric field and this D field, where this D field represents the electric displacement field and it is often known as the electric flux density. So here, the issue with the electric field is that it is the medium dependent. That means if we have some free charge that is placed in some dielectric medium, then of course it generates the electric field, but because of that electric field, the bound charges inside the dielectric medium also fills this electric field. So for example, if we have the free charge inside this dielectric medium, then in that medium, the positive bound charges slightly get shifted to the right side, while the negative bound charges slightly get shifted towards this free charge. And in this process, they creates the dipoles. So effectively, these dipoles cancel out the effect of each other, but the bound charges at the boundary of this closed surface or at the edge of this closed surface will not get cancelled out. And because of that, effectively, we have the negative bound charges inside the medium. And because of that, the net electric field that is coming out of the closed surface of this medium, or in other words, the electric field lines that is coming out of this closed surface will reduce. And that is why, when we are writing the Gauss law expression in terms of the electric field, then we also need to consider the bound charge along with this free charge. But then we have seen that if we write the same Gauss law expression in terms of the D field or in terms of the electric displacement field, then it is the material independent. And in that case, it represents the electric displacement field or this flux density only due to the free charges. So that is why typically in the engineering books, you will find the expression of the Gauss law in terms of this electric displacement field. So this is the Gauss law expression in the integral form, and similarly in the previous video, we have also derived the expression of the Gauss law in the differential form. So using this Gauss law, we can easily find the electric field intensity at any location if the charge or the charge density possesses the symmetry. For example, if we take the case of the point charge, line charge or the infinite sheet of charge, then they have the symmetry. For example, in case of the point charge, we have the spherical symmetry. Because in case of the point charge, if we have the positive charge, then this electric field lines goes radially outward in the all direction. And that is why it has the spherical symmetry. Because from the point charge, at any specific distance, if we see the charge distribution at any angle, then it will remain the identical. So similarly, in case of the line charge, we have the axial or the cylindrical symmetry. And likewise, in case of the infinite sheet of charge, we have the rectangular or the planar symmetry. So for such charge distribution, where this symmetry exists, for such cases, we can easily find the electric field intensity at any location using the Gauss law. So if you recall, then earlier also, we found the expression of this electric field intensity for all these cases using the Coulomb's law and the integral method. But as we have seen, it involves a lot of mathematics. But in this case, we will see that by applying the Gauss law, we can find the same expression very easily. So for that, what we need to do? We need to select the imaginary closed surface that matches the shape and the symmetry of the charge distribution. So this surface is known as the Gaussian surface. And our observation point where we need to find this electric field intensity, it should lie on this Gaussian surface. Moreover, this Gaussian surface should be selected in such a way that this electric flux density is either normal or tangential to that surface. So if this D is normal to the surface, then this D dot ds or the dot product of this D and the ds will become the normal multiplication. And if this D field is tangential to the chosen closed surface, then this D dot ds will become 0. So in that case, our integration will become very easy. So if we select the imaginary closed surface which follows this condition, then using the Gauss law, we can easily find the electric field for the charge distributions which possesses the symmetry. So first, let us take the case of the point charge and let us find the electric field of this point charge using the Gauss law. So let's say we have some point charge having a charge of plus q coulomb. And let's say we want to find the electric field intensity at this point. So for the point charge, we know that this electric field possesses the spherical symmetry. So for this case, we will select the spherical closed surface as our Gaussian surface. And here, the surface is selected such that this point P is also covered along the surface. That means the radius of the selected sphere is same as the distance between the charge and our observation point. So now, as per the Gauss law, we can write the following expression, right? That means the surface integral of this d dot ds is same as the charge that is enclosed by this closed surface. And in this case, this enclosed charge is equal to q. Now here if you observe, then at any point on the spherical surface, this electric flux that is going outward from the point charge is normal to our chosen surface. Or in other words, the area vector of our chosen surface is in the same direction as the d field. So therefore, our dot product will become the multiplication. Moreover, on this entire spherical surface if you see, then this d field will remain the constant. So therefore, we can take it outside. And now, this integration represents the surface area of this sphere. So for the sphere, we know that its surface area can be given as 4 pi times r square. So from this, we can say that this d is equal to q divided by 4 pi times r square. And we know that this d is equal to epsilon naught times E. So this relation is specifically true for the vacuum. And here for a time being, we are assuming that the charge is in the vacuum. So based on this, if we write the expression of the electric field E, then it will be equal to q divided by 4 pi epsilon naught times r square, where the r is the distance between the charge and our observation point. And of course, this electric field will also have the direction, and its direction can be represented by the unit vector AR. So in this way, using the Gauss law, we got the expression of the electric field intensity for the point charge. So similarly, let us find out the expression of the electric field intensity for the infinite line charge. So let's say we have the infinite line charge and it is located on the z-axis. So here we are assuming that it is having a uniform charge distribution, and let's say its charge density is equal to lambda L coulomb per meter. And here let's say we want to find the electric field at the distance rho from the origin. So to find that using the Gauss law, first we need to choose the Gaussian surface. So now in this case if you see, then this line charge has the axial symmetry. Because in this case, this electric field will only change as we move radially outward from the line charge. But at the same radial distance, if we see the electric field intensity, then it will remain same in the all direction. And moreover, since it is an infinite line charge, so from the origin at the specific distance, if we move along the z-axis, then also this electric field will remain the same. So from this we can say that this line charge has the axial symmetry. So here, to find the expression of the electric field, we will take the cylindrical surface as our Gaussian surface. And here, this surface is chosen such that this point P falls on the curved surface of this cylinder. So as I said, here due to the axial symmetry, this electric field or the electric flux density will only have the radial component. And that's why the expression of the D will be of this form. So here, let's say the length of the cylinder is equal to L. So for this length of the cylinder, if we see the enclosed charge by this cylinder, then that is equal to lambda L times L. So we can say that the total charge that is enclosed by this cylinder is equal to lambda L times L. So for this Gaussian surface, if we write the Gauss law, then we can say that the surface integration of this d dot ds is equal to the total charge that is enclosed by the closed surface. And here, this q enclosed is equal to lambda L times L. So here, for this integration, we have the three surfaces of the cylinder. One is the curved surface, and other two surfaces are the top and the bottom lid of this cylinder. So for this curved surface, if we write the integral term, then it can be written like this. So here, the d can be written as d times a rho. And here, for this curved surface, the differential surface area can be written as this rho times d phi times dz. And here, the unit vector for this surface will point radially outward. So that is why we have this a rho term. So similarly, for the top and the bottom lid, this is how the integral term can be written. So here, for the top lid of the cylinder, the differential surface area is equal to rho times d phi times d rho. But here, this area vector for this surface points in the plus z direction. So that is why here we have the plus az. While for the bottom lid, if you see, then the ds will remain the same, but this area vector will point in the minus z direction. So that is why here we have the negative sign. So in this way, we have the three integral terms for the three different surfaces. One is the curved surface, and the other two are the top and the bottom lids of the cylinder. So here if you see, then this arrow dot arrow will become 1. While if we see the other two cases, then this arrow dot az will become 0. So eventually, we will only have the one term. Because here as we have seen, this electric displacement field or this flux density is normal to the curved surface, while it is tangential to the other two surfaces. So that is why these two terms will become 0. And effectively, the first term can be written like this. So that is equal to this lambda L times L. That is the total charge that is enclosed by this cylinder. Now here if you see, then on this entire closed surface, this d field will remain the constant. So here we can take it outside from the integration. And here if we see, then the integration limits will be from phi is equal to 0 to 2 pi, and in this direction it will be from z is equal to minus L by 2 to z is equal to plus L by 2. So if we integrate it, then we will get this lambda L times L that is equal to 2 pi times rho L times d. So here this L will get cancelled out, and we will get this d is equal to lambda L divided by 2 pi times rho. Now we know that this d is equal to epsilon naught times E. So from this we can say that this E is equal to lambda L divided by 2 pi epsilon naught times rho. So in this way, using the Gauss law, we got the expression of the electric field due to the infinite line charge. So as you can see, when the charge distribution possesses the symmetry, then it is easy to find the electric field using the Gauss law compared to the standard integral method. So similarly, now let us find the electric field expression for the infinite sheet of charge. So let's say we have the infinite sheet of charge whose charge density is equal to lambda s. And here, let's say it is located on the z is equal to 0 plane. And let's say we want to find this electric field at this observation point P. So once again, to find this electric field using the Gauss law, we need to choose this Gaussian surface, which also includes our observation point. So here, since we have the infinite sheet of charge and that is also located on the z is equal to 0 plane, so here the xy component of the d field will get cancelled out, and here we will only have the z component. That means for this infinite sheet of charge, we will only have the component of the d field which is normal to the plane sheet. That means here, if we see the expression of the d field or this electric flux density, then it will be of the form dz times az. So as you can see over here, in case of this infinite sheet of charge, we have the planar or the rectangular symmetry. And that is why here we will take the rectangular closed surface as our Gaussian surface. And as you can see, it also covers our point P. So here, this is the intersecting area of this closed surface and our infinite sheet of charge. So let's say this area is equal to A. So we can say that the total charge that is enclosed by this closed surface is equal to this lambda s times A. And now, as per the Gauss law, we can say that the surface integration of this d dot ds is equal to this lambda s times A. That is the total charge that is enclosed by this closed surface. So now, if you see this closed surface, then it has the 6 surfaces. So out of the 6 surfaces, for the 4 surfaces, this d field is tangential. And if you see, then only for this top and the bottom surface, this d field is normal. That means for the remaining 4 surfaces, this d dot ds will become 0. And therefore, during this integration, we need to cover only the 2 surfaces. So if you see the top surface, then for this top surface, let's say the differential area is equal to dx dot dy. And here, this d field can be given as this d times az, because here this d field has only component in the z direction. Similarly, for this differential surface area, if you see, then the area vector will point in the plus z direction. So therefore, here we will also have this az. And similarly, if we see for the bottom surface, then for the bottom surface also, the differential area will remain the same. But now, this area vector will point in the minus z direction. But here, the direction of the d will also be negative. Because here, for this infinite sheet of charge, this d field will be positive in the plus z direction, while it will be negative in the other direction. So therefore, for this field also, we will have the negative sign. So here, this negative sign will get cancelled out, and effectively, we will have the plus sign. And this integration is equal to this lambda s times A. So further, if we write this expression, then it can be written like this. Now here if you see, then on this entire top and the bottom surface, this d field remains the constant. Because here, since it is the infinite sheet of charge, so at the given distance from the sheet, this electric field component will remain the constant. And therefore, this d component will also remain the constant. So therefore, in these both equations, this d can be taken outside. And now, this integration represents the surface area of this top and the bottom side. So here, we have assumed that that is equal to A. So we can say that this integration is equal to d times A plus A, and that is equal to lambda s times A. So we can say that that is equal to 2 times d times A, that is equal to lambda s times A. So here, this A will get cancelled out, and we will have this d is equal to lambda s divided by 2. So now, we know that in the vacuum or the free space, this d can be written as this epsilon naught times E. And if we are in the any other medium, then we will also have the additional term, that is the epsilon r, that is the relative permittivity of the material. But here, for the simplicity, just assume that this infinite sheet of charge is in the vacuum. So with that, if we write this expression in terms of this electric field E, then it can be written like this. That is equal to this lambda s divided by 2 times epsilon naught. And of course, here it will also have the direction. So in this case, it will point in the z direction. And therefore, here we will also have the unit vector az. So if you recall, then earlier also, we derived the same expression using the integral method. But as you can see, using the Gauss law, it can be derived very easily. So I hope in this video, you understood how using the Gauss law, we can easily find the expression of the electric field due to the charge when our charge possesses the symmetry. And on the second channel, I will also try to cover the couple of more examples related to the same topic so that this concept will get clear to you. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe the channel for more such videos.